My name's Jim Stratton. Again, welcome everybody here. Clearly a pretty exciting event we've got going. Looking forward to hearing the talks. Wanted to start out with just a quick introduction about Workday and talk a little bit about some of the data problems that we work on here, some of the data sets that we work on, some of the types of problems we're doing. And actually, Dave, would you mind getting me one while you're over there? Yeah. Thank you. First, just wanted to say a couple thank yous, excuse me, to Liang and Amin on the Workday side, and Edward and Chris on the Skymind side for organizing this. Kim for setting up the logistics, and Kate for marketing support on all this. So I've been with Workday for about 3.5 years. I'm on the tools development side, focusing mostly on scalability, reliability of the service as the service grows. Workday, for those who don't know, we are an application vendor. We're software as a service for financial systems, human resource management, and then associated applications that go along with those, things like payroll, time tracking, recruiting, stuff like that. We're a full stack vendor, so we rent data center space and power, and then we build everything north of that, basically. So I will say we're hiring quite a lot, and we're hiring kind of across that stack. So infrastructure, DevOps, development, application development, tools, platform, and of course data science, which is some of what brings us here. So to talk a little bit more about kind of what are the types of data that we work with, what are the problems that we work on in Workday, it helps to think about what that software as a service means. So if you look at Workday at its core, or the way we represent a business within Workday anyway, it's a graph of objects. And in some cases, those are very, very large graphs because we're serving some of the largest organizations in the world. So we store data about that object graph. We store data about the shape of that object graph. And the use of the Workday application, we're actually just traversing that graph to accomplish whatever the transactions are, whatever the tasks are that make up the serving of the actual application. And so we store a lot of data about those transactions, about that graph traversal, what we're doing within the system, what users are doing within the system. And so that provides us a very large and very rich data set to do a number of different types of analyses against that data. So some of the types of things that we're working on are like comparing the shapes of those different tenants, the different object graphs across tenants. So we can look for things like anomalies, outliers within those shapes that may lead to either functional or performance problems. We can flag those ahead of time and do something about it, right? We're also looking at those transaction logs, allows us to, first of all, categorize, understand what the behavior of users within the system, load against the system in aggregate and against very specific services. And so we're at the moment working on building out some long short-term memory models to allow us, like I said, to categorize, predict what those load behaviors are. When we can get to the point of prediction, we can then use that to dynamically spin up, take down services, understand where we'll have excess compute capacity, things like that. Then when we dig down into the actual objects themselves, we can use things like recurring neural networks to find the basically to understand influences, find causality within changes within those objects. So and allow that to use that to predict things like if an employee is going to leave or if a supplier is not going to pay out, things like that. So pieces of actual business use that we're able to predict causality within those graphs, within the objects within those graphs. And that's what we're building into what we call our insight applications here. And then the last example that I want to use is much more relevant to today's talk, where we're building out a deep learning network to examine what I would call contextual aware OCR. So we can use that in the application for things like expense receipt OCR and invoice receipt OCR, things like that, that then feed directly into the application into contextually aware things that map directly to the application itself. So anyway, that's enough of me rambling on about kind of some of the data problems that we work on, some of the data sets that we work with, and now I'll hand it over to our first speaker, Dave Kale, who's going to talk to us about deep learning networks.
All right. So my name is Dave Kale. So I am actually a PhD student at the University of Southern California, where I work with Greg Versteeg at USC Information Sciences Institute. But I do not say fight on because I am a Stanford alum from undergrad, and that always stays with you. And the animosity between those two schools cannot be overcome. Unless, of course, Stanford starts losing again and USC starts winning, then maybe I'll change my mind. We'll see. But I recently joined Skymind in a limited capacity as a deep learning developer. Now this might sound, and at USC I work on deep learning for healthcare applications. Before I started the PhD, I worked at a children's hospital in Los Angeles. So I have lots and lots of experience with healthcare records, electronic healthcare records data, clinical time series, and then recently I've also been doing a little bit of work with some mobile health data and more longitudinal heterogeneous healthcare data. You might be surprised to hear that I predominantly use Theano in my research. I'm kind of more of a Python guy. So this may seem kind of weird and incongruous. One, that I'm working with Skymind, and two, that I'm here giving this talk. But this will make sense later when I get into exactly what my project is, namely the Scala API. So anyway, there's some information about me up there. We also have a special surprise. The Skymind summer intern, Ruben, just got some really, really good results on a cool project he's working on, DL4J, so he's going to do a demo at the end. Deeplearning4j is a open source deep learning framework on the JVM, so it's in Java top to bottom. Now that's a little misleading because like all the other deep learning frameworks, what it's really doing at the lowest level is generating primitives in either like C or Fortran or CUDA or whatever to do all the math efficiently. But sort of the abstraction layers on top are in Java, and it runs on the JVM. Skymind is a startup that's doing deep learning for enterprise and kind of fighting the good fight against the Python deep learning mafia. And it was founded by Adam Gibson, who is a prodigy and one of the smartest people I've ever met. Like I don't think he sleeps. He's on the Gitter channel like 24 hours a day, and he seems to know something about everything. It's really, really impressive. And then our fearless leader is Chris Nicholson, who's over there. And we have some other Skymind folks here as well. Here's the outline of our presentation today. I'm going to give you an overview of deep learning, and I'm going to sort of give it to you from my perspective, like what I think is the most useful way to think about deep learning, because it's poorly defined. It's obviously deep learning is more a marketing phrase than it is like an actual set of techniques or a discipline or a science. And I think there's a lot of noise about it. So I'm going to sort of give you my the way I think it's most useful to think of it. I'm going to give you sort of a brief tour of DL4J. I'm going to talk about scaling up DL4J with using things like GPUs as well as the Spark API. And as you'll see, this is actually fairly straightforward and trivial. There's like minor changes to the code. I will make some they asked me to talk about DL4J versus other frameworks. I'm going to give very, very brief comments about this. I don't think it's that useful to go through it in detail. Rather, I will tell you sort of the situations under which I would recommend using one or the other. I'll give you a brief preview of the DL4J Scala API, which is what I'm currently responsible for. And then Ruben's going to show you something really, really cool. So what is deep learning? When folks talk about deep learning, they sort of, there's a lot of hand waving and talk about, biologically inspired computing and neural nets and neurons and, hidden units and dropout and all that kind of stuff. Those things are all technically true. I don't know that it's necessarily the most useful metaphor for deep learning. In my opinion, the most useful metaphor is we start with some input, And deep learning is really just sort of compositions of functions, usually deterministic differentiable functions, some of which are parameterized. You know, they have weights and biases and things like that. Sometimes they're not. Sometimes they're just sort of deterministic functions like a max pooling or something. But they all compute transformations of the data. So you have an input X and what you get out is a Z. And we compose multiple of these. So maybe the transformation from one layer gets fed into the next layer. Maybe it gets fed into another layer. Eventually, we emit some output that we want to get. We can actually have multiple paths, so you can sort of have like elaborate computational graphs. And so that's why sort of the old school notion of the neural network starts to kind of fall apart and it's more useful to think of things as, think of deep learning as just composing functions, okay? And just doing useful transformations of the data that make it easy to solve the task that you want. The key thing here about neural networks in general and deep learning and all this kind of stuff, the most sort of useful thing to think about is that this architecture for transforming your data is end-to-end differentiable with respect to your parameters. So if you remember your calculus, you can take derivatives. And you can train by defining a set of targets that you're trying to emulate, so that's the T down there. And then you just write down some loss function. And your loss function is basically supposed to describe the semantics of how it is to do well at your task. You know, you get into the weeds of like, do I need cross entropy or L2 loss or blah, 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 blah. At the end of the day, the loss function is just a metaphor for, you know, what does success look like in whatever task it is you're trying to solve. And to some extent, especially sort of in the era of deep learning, this thing in a lot of ways is kind of the most important thing because you can have the most elaborate deep neural net and you can be using the latest and greatest because Yoshua Bengio said you should. And if you're applying it to a task and you're using the wrong loss function or your loss function doesn't properly express what you're really, you know, what the essence of solving your task looks like, not going to get very good results at the end of the day. And of course, we train by applying gradient methods. We use the chain rule. We take derivatives. If you remember the chain rule from your calculus class, basically the derivative of a function with respect to something, you basically end up with the derivative of the first function, and you end up with a product of a bunch of derivatives. All right, so. That's why I think it's useful to sort of get out of the weeds about like convolutions and neurons and all that kind of stuff. Just think about this as an architecture that is composed of functions and that it's end-to-end differentiable. And that is like the magic of deep learning. You can train them end-to-end. There's a professor from UT Austin who works on computer vision and natural language whose name suddenly escapes me. He said this in a talk. I'm stealing it straight from him. He was very skeptical about deep learning. He liked other methods. Naturally, his students pushed him into using them. But he said what he came away with was these kinds of neural net architectures are basically the only model where you can wire it together to do what you want end-to-end and train it end-to-end instead of having to train each piece in isolation and then glue them together and get an accumulation of errors. Now, granted, a lot of times we want to train these things piecewise, but then at the end, you put them all together and you train them end-to-end. So that, I think, is the most useful metaphor. So what are some examples? There is ye old neural net architecture, the multi-layer perceptron. This is a robust, powerful, nonlinear function approximator, to use some jargon. Typically, they have 0 or more fully connected or dense layers in the middle of hidden units. A special case of the multi-layer perceptron is just logistic regression, a linear model, where you have 0 hidden units, okay? So there isn't like sort of a magic gap. I mean, there is somewhat in terms of performance for many problems, but there isn't really a magic gap between linear models like logistic regression and neural nets. A linear model is really just a special case of a neural net with 0 hidden layers, all right? So now we do finally get into the weeds of neurons. A neuron is basically sort of, in the most classic definition, you're multiplying some weights times some input, maybe adding a bias, and then applying some kind of element-wise nonlinear function. Classically, this would be a sigmoid. More recently, people use things like rectified linear units, and then the research community proposes all kinds of crazy things that will give you, 0.000001 improvement on MNIST, and then you get a NIPS paper, okay? But in general, I think for a lot of problems, you're probably using rectified linear units, maybe sigmoids, and things like that. In general, what do you use an MLP for? You use it to predict some target Y from a fixed size, not too large, input X that doesn't have any kind of special structure that you want to exploit. The reason I say fixed size input, if your X varies in size, like if you're working with like sentences of different lengths, well, you can't apply a neural net to that directly. I mean, there's kinds of ways that you can apply it to it. There's hacks, sliding window, and stuff. But this architecture is really designed for fixed size inputs. The reason I say not too large is that with really, really large inputs, you end up having tons and tons of parameters that you need to fit. And very frequently, in cases where you have large inputs like that, there's probably some structure you want to exploit, which we'll get to in a moment. What are some examples of things you can do with this? Every single deep learning framework has a tutorial where you apply this to MNIST, everyone's favorite data set to overfit their methods to, but happens to be sort of a good place to get your feet wet. One thing you could imagine applying it to is modeling the risk of mortality in patients with pneumonia, for example. There's actually an excellent paper from 20 years ago by Rich Caruana, who's now at Microsoft Research, where he does just that. A variation of a multi-layer perceptron architecture is an autoencoder. This is kind of just a special case where we don't have this separate target Y. Rather, what we do when we're training is we just use the input as the target. And the goal here is to learn some kind of succinct representation in some middle hidden unit. Let's call that Z. We'll call that sort of a latent representation. And the goal here is to be able to learn a succinct latent Z that the model can then reconstruct the input from. And these are kind of useful for sort of just learning representations. What these were really, really used for a lot, let's say starting in about 2006 through about 2012, was doing pre-training of neural nets, where let's say you had hundreds of thousands of images, but only 1% of them were labeled. People found that you could pre-train an autoencoder. You could train an autoencoder on that data, use those parameters to initialize a multi-layer perceptron that you will then train to classify on the 1% labeled images. That pre-training, unsupervised pre-training, has largely been abandoned because for most problems people work on, they find they have enough labeled data. Healthcare, by the way, is a domain where that typically is not the case. So these types of methods remain somewhat relevant there. Now, one place where these become more useful is if you wrap a probabilistic framework around them. You basically put a prior distribution on your latent factor Z, and then you train it like with, let's say, a restricted Boltzmann machine or a variational autoencoder or something like that. Then you can actually generate new X's. You can generate data by sampling from your prior distribution Z and then applying your neural net and getting X's. That's something you can't do with a deterministic autoencoder because you have no way to get your Z's that you start from. So you need a prior. You need a sort of a generative model of that type. Okay, so I mentioned data with special structure. I mentioned, if you have a really, really large input, let's say a huge image, high-resolution image, and you want to train a classifier, maybe you think, all my images are the same size, I can use a multi-layer perceptron. But actually, probably you'd be better off using something called a convolutional neural net. And basically, the intuition of the convolutional neural net is sort of twofold. First, there's sort of local patterns that are relevant, and you want to exploit the kind of local regularity. So things like edges or sharp changes in contrast from bright pixels to dark pixels and that kind of stuff. Those things seem to be really useful. We know they're useful in computer vision because decades of computer vision researchers invested probably hundreds of thousands of hours in trying to design better edge-based features, and then eventually got clobbered by neural nets. But basically, there's sort of this there's this sort of locality in there's this local structure in images that's well known. So convolutional layers are basically just filters that you kind of apply, that the model applies in sliding window fashion to convert the data. And the filters that they tend to learn look like edge detectors and corner detectors and contrast detectors and things like that. So the filters are sort of exploiting the spatial and local regularities in the data, but they also preserve the spatial relationships. So like once you've filtered the data, the filtering of the upper left-hand, the output of the filter on the upper left-hand corner is still spatially next to the output one step over. Whereas with a fully connected neural net, everything becomes entangled after the first dense layer. So the other thing that convolutional neural nets do is they apply subsampling layers or pooling layers. And these basically reduce the resolution of your image. And in doing so, what they allow you to do is get a certain amount of translational invariance. So let's say you want to detect cats in an image, and you don't really want to have to try and build a model that has to be aware of the fact that the cat might be in the upper left-hand corner or the lower right-hand corner. You kind of want the model to just sort of be able to find the cat wherever he happens to be, at least within sort of certain small shifts. So subsampling allows us to do that. It gives us a certain amount of translational invariance. Okay? So what are some examples of cases where we have this kind of structure that we'd want to predict? A 2D example, classifying images of cats, as I mentioned. So you're doing sort of 2D convolutions. A 1D example that's sort of slightly less common would be time series. In particular, sort of if you have short time series, but you think that you have sort of temporal invariance. So like, let's say you want to diagnose a patient from their last 6 months of data. You want to predict, do they have, some kind of like diabetes or some kind of metabolic disorder? And you don't really care where their abnormal lab test was. If it was in month 2 or month 1 or month 3, it doesn't matter. You want the model to be able to predict that they have. You don't want it to have to take temporal order into account. In that case, a temporal convolutional neural net with 1D convolutions along the temporal axis is a good choice. And in fact, there's a really excellent paper out by a colleague of mine from New York University on doing just that. There are also special cases. So a typical convolutional neural net architecture has a dense layer at the top, a multi-layer. So basically, you have a set of convolutions you apply to the data that are learned, and then they get fed into a multi-layer perceptron. There is also something called a fully convolutional network architecture that has no MLP at the top. You can think of this, whereas the MLP is a nonlinear function approximator, the fully convolutional network is a nonlinear filter that you're learning. And the use cases for these are maybe somewhat limited, but what they can be useful for is training an image segmenter from weakly labeled data. So let's say you have images, you want to find cats, you want to label pixels as belonging to a cat or not, but you didn't go through and label every pixel as being a cat. You just have image level labels. Well, in that case, a fully convolutional network would actually be able to do a reasonable job at that problem. So convolutional neural nets, basically, you can think of them as having these filters that get applied that are parameterized, differentiable, and trainable from data, and they exploit sort of local structure in your data. So let's go on to another example of structured data, and that would be sequence data. And the models that are classically used for this would be recurrent neural networks. Recurrent neural networks are really just, you can think of them as a multi-layer perceptron where we add a recurrence edge between the hidden units. And we're applying them to input sequentially. And the hidden unit activations from the previous step or previous application, let's say time t, gets persisted and fed into the hidden units at the next step, t+1, okay? So there's recurrent edges. This recurrent edge gives you basically a form of memory for capturing dependencies. And in principle, you can learn really, really long-term dependencies. In practice, this is very difficult due to problems known as vanishing gradients and exploding gradients. To solve those, people have designed much more elaborate recurrent neural networks. It was mentioned previously, long short-term memory networks. There's also gated recurrent unit networks, and the research community has developed dozens of these things, and recent papers show they all perform about the same. But the main sort of trick here, the things that give you the real power here, is having a recurrence that is not, that basically your hidden, you have sort of, you decouple your hidden states. You have a hidden state that gets kind of emitted and passed to other parts of the network. Then you have an internal hidden state that is used for persisting information over long periods of time and passing gradient information backwards during training. And that persistent hidden state is basically a mixture of the previous hidden state plus some other activation you've computed. And that's, I think in Jürgen Schmidhuber's lingo, he calls that the constant error carousel. Usually they're just called sort of memory cells. And that's sort of like, that is the thing that gives the long short-term memory network its power. So what do we use RNNs for? Let's say you have sequence data, like let's say natural language, video, time series, whatever. In particular, let's assume that your objects are variable length or variable size. If they're all short and fixed length size, maybe you should just use a multi-layer perceptron, much easier to train. But in general, language, sentences are all different lengths. Patients in a hospital may be in the hospital for 12 hours or 3 weeks. So these cases where you have this sort of sequential data, and in particular they vary in length, recurrent neural network might be a very, very good choice for your problem. These are among the most flexible and sort of powerful learning algorithms that we have today. They're also among the hardest to train. RNNs, as I mentioned, are very, very flexible. There's all kinds of different input to output modeling that you can do. So there's diagnosing patients from temporal data. I have a paper on this at iClear in 2016. This is sort of a many-to-one problem. So you have a sequence of observations of the patient while they're in the hospital, and then you just want to spit out probabilities about whether the patient has a disease. There's predicting the next word or character. This is language modeling. This is sort of one variant of a many-to-many problem. There's also, you could generate a beer review from a category and a score. This is a talk that I, along with another Skymind employee and a colleague from UC San Diego, are going to give at Stratton NY next month. You can just feed in a category of a beer and a score and some other information, and then it will generate a natural language review for it that looks a hell of a lot like the kinds of things that you see on Beer Advocate. So that's sort of a that's kind of a one-to-many problem. That's kind of a fudge because it's sort of also many-to-many because the words and characters that get generated get fed back in. But I think it's properly thought of as one-to-many. Then there's machine translation, so translating, let's say, from English to language, English to French. That is also sort of a many-to-many problem, where typically what you do is you have an encoder network that encodes your English language into some hidden state, and then you have a decoder network that then evolves that hidden state and spits out French. So RNNs, very powerful and flexible. You can do a lot of damage and cause yourself a lot of pain with them. We can also get crazy with architecture. So what about automatically captioning a video? Recall, all we're doing is composing functions that transform inputs, okay? So you might think like captioning videos, that seems complicated and weird and hard. It's really not, actually. All you have to do is think of your video as a sequence of images. Now we know convolutional neural nets are good for images because images have sort of locality, local structure and spatial structure. So maybe what we want to do is we want to have a convolutional neural net that processes each frame of the video one at a time. Then the input of that gets fed to what kind of model would we want to use for like a sequence modeling problem? Oh, an LSTM or an RNN of any kind, a recurrent neural net. And then we want to generate English language, because that's what we're doing when we're doing captioning. Well, how might we do that? Another recurrent neural network that is then doing the language modeling problem. So we just composed convnets with a few different recurrent neural networks. Note, you could do this with DL4J today. I don't know, there's no example in the repository of this, because you got to come by the data. But all the pieces are in place. You could easily do this. And it is doable. There's a paper at NACL 2015. Now, when I say doable, I don't mean closed captioning people are out of a job. No, like many things, it's doable sort of within whatever invented metrics the researchers working on these problems have, where they show like we've set the state of the art, and the state of the art is well below human performance. But still, there's traction, right? Like there is an architecture that could hypothetically solve this problem. Like I think I've got some craziness going on here. So yeah, so just keep in mind for your particular problem, just you're composing function transformers. And you want to think about the nature of your data and the nature of the task that you want to solve, okay? Another route you can go, you don't necessarily get crazy with your deep learning, neural net, whatever architectures, but you can get crazy combining them with other tools that we know of from computer science. So these are a couple of figures from the Nature paper that describes AlphaGo. And you know, as you know, AlphaGo beat like the world Go champion. And this was previously believed to be a decade away, because Go is thought to be a much harder problem than, say, chess. This, of course, was celebrated as a triumph of artificial intelligence and also hailed as like the end of humanity. AI, deep learning, beat the human beings, the singularity is right around the corner, et cetera, et cetera. None of this is true. While it was a very impressive achievement, and I don't mean to minimize the amount of engineering effort that went into that and the ingenuity of building that. Nonetheless, it really is just a simple combination of models that we know work very well for this type of data, so convolutional neural nets applied to the game board, represented as basically an image with pixels representing pieces. And they just had 2 different neural nets, one for estimating, one that is a policy network, so it's estimating the value for each potential position. And then also one for, one for estimating sort of the probability of a move, the other one for estimating the value of a particular move conditioned on a particular board, right? So a value network, a policy network, but both just convolutional neural nets. Now, immensely complicated, very deep convolutional neural nets, nonetheless, just convolutional neural nets, and then they combined it with something called Monte Carlo tree search, which is something that has literally been around for a decade or more. There's a really good blog post by John Langford on this where he says, you know, this is like a huge, this is in some, practically speaking, empirically, it's a big step in reinforcement learning, but in terms of actual reinforcement learning, it's not that big of a step because there's no new reinforcement learning here. These are all tools that we knew existed. Again, by no means was the engineering required to do this simple, but I'm just saying, the pieces exist to do this. This isn't magic. You could do this as well. If you had 30 million moves, the database of 30 million moves, and all the computing power and all that kind of stuff. And in particular, since now they've described it in such wonderful detail, you can go download the moves, and you could start working on this if you wanted to. Probably you won't be as successful as them, but still. The pieces are in place. You can do this. All they're doing is combining these nonlinear function approximators, convolutional neural nets, with algorithms that are known to work pretty well from computer science. Another example of this, you can combine deep learning with Bayesian methods. So let's say you care about uncertainty. For example, if your model is saying that this patient's going to die, you'd like to know how confident is the model about that before you do anything about it. There's a class of models called variational autoencoders that basically allow you to do this. So I want to give you some sort of practical sort of implications of the deep learning era. You know, sort of what does this really mean, the brass tacks? Architecture design and hyperparameter tuning have replaced iterative feature engineering. I feel like 5 years ago, people doing real-world industry machine learning were spending most of their time inventing new features, running experiments, checking the validation set, seeing how much lift they got, deciding whether to keep those features, trying some new features tomorrow. Now, instead of doing that, what you do is you make up an architecture and do basically the same thing. Train your model, look at the validation performance, see if you get lift, try to decide, should you add a couple more hidden units to this layer? Should you add another layer? Should you add a convolutional net? Or should you add some more filters to your convolutional layer, et cetera? So in some sense, it's more satisfying. At least personally, I find it more satisfying. I like architecture design better than engineering features. At the same time, your job hasn't gotten much easier because you're still kind of doing this like futzing around with like, I don't know, I'll add another hidden layer. What will that do? Well, we'll see what the validation performance says. It is a little bit easier to do if you do hyperparameter tuning, if you systematize your search for a model. So in some sense, we're maybe a little bit closer to sort of auto magic machine learning and all of us being out of a job. But we're not there yet. I think we've got at least another good 10 years before we have to start worrying. I'm just making that number up. For all I know, we might be out of a job next year. I don't know. Actually, I think one implication that I think is really important is that with neural networks and deep learning, it's a lot easier to transfer knowledge from one problem to the next. When I say transfer, I mean it in two senses. One, there's direct transfer. There's literally, you can go download the like best performing ImageNet convolutional neural net classifier and then like fine tune it on some other image data and get state-of-the-art results. So you can do direct transfer learning, but there's also indirect transfer where you can draw analogies about problems across different tasks. And you can think like, hey, recurrent neural nets work well for this. Maybe I want to apply it to this other data set that looks actually a lot like this problem. And I bet an architecture that looks kind of like this other one will work well. Neural nets are often much better able to leverage really, really huge data, like the kind that it sounds like they have at Workday. So that's a good, probably you'd be better off starting off with like neural nets than you would be like doing linear models and trying to make up a bunch of features. None of these things are true, okay? Your big data problems will not be solved magically by deep learning. The machines are not going to take over anytime soon. And Ray Kurzweil will not be uploading his brain to the internet before he dies. I don't care how often he asserts that is the case. I highly doubt it. So let's talk about a DL4J architecture for image captioning. This will look a lot like the video captioning one. And there are examples for doing, no, maybe they're not, actually. But I'm sure we could make one pretty easily. So let's suppose we have this image from an upcoming episode of Girl Meets World from the Disney Channel, which my wife is a writer for, which features the wedding of Sean and Maya's mom, Katie. That's her name. Katie is her name. So let's suppose we have that image, and the caption we want to spit out is Sean marries Maya's mom, Mr. Feeney officiates. So first DL4J component that you'd want is like a sequence record reader, actually just a record reader. It would be a sequence record reader if you're doing video. Then maybe you might feed your images into a convolutional neural net, and DL4J has a convolution layer. And then you might flatten that and feed it into a dense layer, so a multi-layer perceptron type thing. Then the output of that would get fed into a recurrent neural net. So DL4J has the Graves LSTM layer. And then that model will spit out a caption during training. Maybe it says, Sean marries Mr. Feeney, and some lady is there. Well, that's not quite right. And by the way, there's an RNN output layer that you put in there to spit out this. So we want to correct this model. So we feed the prediction and the true caption into a loss function. And DL4J uses a linear algebra library called ND4J, which provides lots of loss functions. In this case, you would just use cross entropy because you're basically looking at predicting the next word or next character, which is basically a multi-class prediction problem. All of these things get glommed together in a architecture or a model. So that would be, in DL4J, you would call that this would be a multi-layer network. But there's also computational graphs that allow you to do arbitrary architectures. And then finally, for training, you need to do some kind of optimization using backpropagation. So DL4J has a broad set of optimization algorithms that you can use, including sort of stochastic gradient descent, which is sort of the main one you might use, but also LBFGS and a few other things. So basically, all the pieces are in place to do this. Likewise, for doing video captioning and probably most other sort of really, really interesting, cool AI-like tasks that you'd want to do, including reinforcement learning, as Ruben will show you pretty soon. So what is the DL4J ecosystem for doing scalable deep learning? So first, there's sort of the core. This includes sort of an efficient NumPy-like numerical framework, ND4J. ND4J provides backends in sort of a variety of your favorite linear algebra libraries like Atlas, as well as CUDA, so we can run on the GPU. And we can also do multi-GPU as well, okay? There is a Spark API that wraps the core DL4J classes. Designing and configuring your model is identical. So when you say, I want to train a convolutional neural net with all these layers, you don't do anything different if you're just going to train on one machine versus use Spark to train on a cluster. It's exactly the same. I will show you some code in a moment to show you sort of the minimal differences. Right now, what the Spark API provides is data parallelism for training your model in parallel. So this scales to massive data sets, but it still requires your model to basically fit on a single machine. So we don't have model parallelism at the moment. But it does, it can greatly accelerate your training, especially for really, really big data sets, especially for data sets you can't store on a single machine. And then there's a library called DataVec, which is the one where like the record readers and things like that come from. Also compatible with Spark RDDs, okay? Finally, I want to mention Arbiter. Arbiter is a platform-agnostic model evaluation framework. So I mentioned doing hyperparameter tuning is very, very important. You do not want to be manually sitting there trying one model at a time, watching its performance while you're there, and then tweaking the parameters a little bit, starting the next one. Trust me, having done this as a grad student, you don't want to waste your time doing that. You want to use some kind of systematized way to do this. The DL4J ecosystem has this as well. There's Arbiter. Arbiter can be used with other machine learning frameworks if you want. And right now it provides randomized grid search, which is sort of the simplest way to optimize. Don't do grid search with neural nets. Do randomized grid search. If you want to spend the time, invest the time to do Bayesian optimization, great. Randomized grid search sort of gets you 95% of the way there. To do scalable deep learning with the Spark API, We use sort of the downpour stochastic gradient descent approach from, and I omitted where it's actually from, but it's from a Google paper lead author, Jeff Dean, from a while ago. I'll add, I assume we're going to share these slides. I'll add the reference when I do that. Data parallelism, so the training data is sharded across workers. The workers each have the complete model, and they train in parallel on sort of their own, on disjoint mini batches. So, you know, as soon as they start training, they start diverging, right? What happens is you also have a parameter averaging master server that has sort of the canonical version of the model, right? So as the workers are training and computing gradients or parameter updates, they're reporting them back to the master server, and the master server is accumulating these, and then it will finally sort of, when mini batches are all done and the workers are all done with their current training, it will compute updates to the sort of the canonical model, and then send messages to the workers reporting the updated parameters, and then you start the whole thing again. And basically, it works using iterative reduce. Yeah, so there we go. Basically, that's the trick. It's actually conceptually a very, very simple algorithm and seems to work really, really well. And in fact, when you're doing stochastic gradient descent with large data sets, this kind of parameter averaging sort of can sometimes give you better performance than doing sort of serial stochastic gradient descent. It provides a certain amount of regularization. So you probably can't read this, but this is an example of configuring a LeNet image classifier, which is a fairly robust, not necessarily state-of-the-art, not the most complex, but a robust convolutional neural net architecture that was first described by Jan LeCun, I think like 20 years ago, as he would remind you. You can see that, or maybe you can't see, I don't know. You can see that DL4J uses the builder pattern. So that way you don't have to, you know, work with constructors with dozens of potential parameters. And you can see you're basically, you set things like sort of how you're going to initialize your weights, what distribution you're sampling them from, what's your optimization algorithm, stochastic gradient descent. You add one layer at a time. So first layer is a convolution. Next layer is the subsampling, so max pooling, another convolution, another max pooling. Finally, flatten things and shove it into a multi-layer perceptron. And then at the end, you're going to spit out, you have a softmax classifier that's spitting out which class do you think this image belongs to. You specify your loss function here. We're going to use negative log likelihood or multi-class cross entropy. We're doing backprop. We're not doing pre-train. You have to give it some information about the size of your input since you're working with a convolution. And then finally, so this is your model configuration. Then you call your constructor for your multi-layer network, pass in the configuration, and then you've got your model, you initialize it, and then you proceed with training. So on a multi-GPU server, what does that look like? So basically, you access your CUDA environment configuration and just tell it, we want to do, I have a server with multiple GPUs, please use them. And you can set some other things like maximum device cache itself. You can tell it that cross-device communication's fine, et cetera. You configure your network and initialize it, and then you proceed with training. And basically, you wrap your model in this parallel wrapper, and that sort of allows it to utilize the multiple GPUs. You configure some things, you call build, and now you have your model configuration, and then you pass it into your model constructor and train as before. Suppose we want to train LeNet on Spark. So as you can see, minimal changes. Basically, we do some Spark setup stuff. Ignore this stuff about image transforms and whatnot. This is kind of superfluous. We have to set up our parameter averaging master, okay? So our server that does the parameter averaging and maintains the canonical version of our model. And you set some things about sort of how often you want your workers communicating with your master, how large your batches are, how often you average your parameters, et cetera, okay? And then finally, you do the whole model configuration stuff. That's what's going on right here. And then all we have is we have this wrapper around the multi-layer network, the core DL4J version. It just wraps it. You pass in your model. You pass in the training master that we configured up here. and then you call fit on your data, just like before. So you can see going from training, let's say, a toy neural net on your laptop with no GPU to a server with multiple GPUs so you can get some additional efficiency, to training on a Spark cluster requires only sort of minimal changes of code. Obviously, it's much more complex than that. You have to think about architecture and like size of your cluster and things like that. But you're not using a radically different API. And it certainly isn't the same as, trying to crowbar TensorFlow into Spark or something like that. Okay, so they asked me to comment, as I mentioned, on DL4J versus other frameworks. I don't want to spend a lot of time on this because there's lots of other good places where you can go read the sort of bit-by-bit, blow-by-blow comparisons, and sort of comparisons that concern features like which one has the model that appeared in NIPS 3 months ago or got posted on archive yesterday, or features like which one has this architecture or which one's faster and stuff. Those things are constantly in flux, and they're not important unless you're like a grad student trying to get a paper out next week, right? So I don't think those are worth spending some time on. But what I can tell you sort of from my point of view, when would I use which? Because as I mentioned, I'm a grad student and I use Theano in my research, right? If you're doing custom layers and loss functions and things, then you're probably going to want to use Theano and TensorFlow because they give you symbolic differentiation. They give you the ability to sort of write down a mathematical expression and then say dot grad and get the gradient, and then do stochastic gradient descent, etc. So if you're like a grad student trying to publish a NIPS paper, if you're trying to win a Kaggle competition with like an OpenAI model that got posted on GitHub along with an archive paper last week, or you just want to prototype, let's say you're not either of those things, but you just want to prototype an idea, and you don't want to go and derive the gradient by hand and try to implement it yourself. You would rather sort of prototype it, see if it works on a small data set, and sort of de-risk it before you go and invest the effort in implementing it. Then, this is where you want to live. But not only, as I'll mention, you can use all these tools together if you want. If you want to use published computer vision models from the Caffe Zoo, you should probably use Caffe, at least for right now. That'll change soon. If you're a Python shop and you don't mind being held hostage to the Google Cloud, at least in the future, you should use TensorFlow. That is where they're going, folks. TensorFlow is designed to lure you into using Google Cloud, okay? They're pretty transparent about that, too. If you're like a Java big data shop and you're using the Java ecosystem, Hadoop, Spark, et cetera, then you should be using DL4J. You should not be trying to crowbar these other things in. If you want robust data pre-processing tools, because you don't want to have to write your own code to like manage, process images and flatten them and turn them into vectors, et cetera, DL4J, I think, among the packages is putting the most effort into that. Because they know for like real-world machine learning, where you're not fiddling around with toy data sets, this is the biggest pain point for machine learning people. And they have a really, really nice set of tools for that. As I mentioned, there's good news. Everyone wants to compare and make a choice. This is a false choice. You can use all these things. In particular, let's say you're a Java shop and you need to use DL4J in production, but as I said, you want to de-risk some clever model you've invented and make sure that it actually works before you invest the engineering effort, or you go on the Gitter channel and complain to Adam and try to get him to implement it for you or something. Prototype it in TensorFlow or Theano, or maybe use Keras and those kinds of things. And then you can convince yourself it's worth the effort. Then you can go back and add it to like DL4J. Okay, so it's a false choice, as most things are. Most cases where people try to convince you it's either or, it usually isn't. As I mentioned, you can have your cake and eat it too. And the reason for this is we're working on a Scala API for DL4J. And of course, one of our goals is to satisfy sort of the popular demand for this. People want it. But the other reason we want to do this, sort of my mandate that Adam gave to me, and this is the reason I'm doing this, even though, as I said, I use Theano in my research, is we want to build an API for DL4J that as closely as possible emulates the Keras user experience. Because that will minimize friction between going from Keras to DL4J or the other direction. So you see a model that some PhD student created, and he added the layer to Keras. And so Keras has an example, and you're like, oh, I'd really like to try that, but I'm using DL4J. We're building an API that will allow you to very easily go from the model they specified to the model to specifying it in DL4J using this API. Also, we are collaborating with Francois Chollet, the Keras guy, on agreeing to a common model storage format and then building tools in both DL4J based on this API, as well as Keras to read that, so that you can train a model in Keras and then go and apply it in in a DL4J ecosystem. Okay, so side-by-side comparison. So over here we have a 2-layer multi-layer perceptron to classify digits in MNIST using sort of the standard DL4J builder pattern. Here on the right-hand side, this is what this looks like in Python and Keras. So you specify a sequential model. That's their version of a multi-layer network. You say, give me a dense layer with an activation that's a rectified linear unit, add some dropout, another dense layer, and then a dense output layer, and then that's our model, compile it, and then train it. This is what the API looks like in the Scala, or this is what it looks like in the Scala API that I'm developing right now. So you can see, looks like DL4J up here a little bit, but the actual model specification looks very, very similar to Keras. So add a dense layer, so we have a sequential model, add a dense layer, add a dense layer, add a dense output layer, specify your loss function and stuff, and how you're going to optimize while you're training at the compile step, and then call model fit. So, and you can see it's not that hard to go back and forth between any of them. So we're building a bridge between DL4J and Keras. And at the same time, killing two birds with a stone, there will also now be a native Scala API. And of course, it's wrapping the DL4J primitives, so any sort of optimizations or improvements or new layers that get added to DL4J will immediately be added into the Scala API as well.
So my name is Ruben Fizel, and I built RL4J, which is a nice acronym for Reinforcement Learning for Java, or the same than DL4J. And I'm going to start by describing briefly what is reinforcement learning. So reinforcement learning is a way to train an agent to learn to play optimally in an environment. Well, this environment is more formally described as a Markov decision process, but this is not very important. The thing you have to remember is that it's very versatile and that you can describe a lot of environment with it, including most of the games, well, we all know. And AlphaGo is an example of it, so you can describe Go. So why is it called reinforcement learning? It's because you learn from having an advantage from a strategy. So you learn from getting more rewards than before. And those rewards, they help you knowing what is the optimal strategy. So, by example, in the game of Go, you have a reward at the end. If you win, it's +1, and if you lose, it's -1, obviously. And so reinforcement learning, it can work on memory, but it can work on neural network because they use them as a universal function approximator. And those functions they are used to quantify how much an action is worse, in the sense that if it's a good or a bad action. And by example, you're in a video game and you have to decide if you have to go right or go left, then you have to quantify how much this action is worse, and you can use a neural network for that, as long as you train it properly. But good for us, there is an algorithm that is called Q-learning, and this Q-learning algorithm help you define the right way to train a neural network to have the right approximation. So all the code is available on GitHub. It's private, but it's soon going to be released. So yeah. So this is a scheme of a Markov decision process. It's just one state with actions that help you translate into other states. It's a stochastic process, so you have probabilities. So I'm going to go fast. So this is the fact that you're in an environment, you get rewards, and it's called a feedback loop. So RL4J is compatible with GIM, the stack of OpenAI to compare algorithms. And not everything is ready because we use a HTTP API, but most of the things are able to train. So what I did is I trained an agent on a problem that is called card pull that I'm going to show you. And so yeah, as you can see, so the goal is to move along a line and to stay as long as possible up. And this is at the beginning of the training, and you see that the card pull is doing terrible because it's just moving randomly, and the pole kind of fall, and it's reset each time it falls. That's why you see all the jiggering. And here you see that the card pull is like adjusting very finely to the momentum, and the stick actually never fall. It reset when the timeout reach. So that's, and usually when you train by reinforcement learning, you want to check that your agent is actually learning. So you don't just check the videos, you actually check a graph. And here you have a graph of the cumulative rewards, which is very useful to see that actually at one point it converged into the optimal solution. You can use also other stats, which the most important one is the score of the neural network, which means that the neural network is actually converging, and the mean Q, which is the mean worth of an action. And well, card pull is very nice, but I guess you're not here to see that. So if you combine, as said by Dave, if you put up the right tools and the right primitive, you can do something even cooler, which is you can try it on real video games like Doom. And I'm going to show you. So this is the beginning of the training. He played very badly. And the goal of the game is to reach the end of the hole. And this is the end of the training. So it's trained based on the pixels only. So no states, no low-dimensional representation, only the pixels. And it learns to actually avoid everyone. It kills one very fast. I'm not sure exactly how it does it, but it does it. And, well, so, well, that was a cool demo. Thank you, everyone.
Nice work, Ruben. This poor guy slaved away on that all summer. So I'm done. I'm just going to throw up one last, conclusion slide. I want to thank you. I think we're doing Q&A after, because next we have Dr. Leo Tam from NVIDIA talking. But here's some links. You can, you're not going to write them down, but hopefully we'll share the slides and then you'll have them. So, but the Skymind website, the Deeplearning4j website, my personal information, and my research website as well. So thank you very much.